It's just so tempting. Procrastinating, but don't do it. All right, we're looking at a spring launching a block, which is our last example. So we have a spring force constant 500 newtons per meter with a block that is 5 kilograms pushed up against it, so the spring is compressed a distance of 0.3 meters. Frictionless side of the block is in contact with the table. So when the block is released at point A, the block slides along the table without friction. The block then becomes a projectile at the end of the table. While a projectile, the block rotates so that it lands without bouncing at point C on its gray friction-full side. The block slides 3 meters to rest between points C and D due to friction. A lot of stuff going on here. Make sure you fully understand the situation. This is a lot of information given to you. So just take your time with it and underline what you think is important if it were on a printed piece of paper. What's the speed of the block at point B? Well, if this is frictionless, then whatever energy we started with should give us whatever energy we end with. And at point B, if we say y equals 0 at this table height, then the only energy it's going to have is kinetic energy. Nothing else is acting on it. So in the beginning, at point A, we have spring potential energy. 1/2 kx squared with B kinetic energy 1/2 mv squared. So the block has the same amount of gravitational potential energy, so we're ignoring that. Our equation becomes 1/2 kx squared equals 1/2 mv squared. Solving to get speed at point B, we get the square root of k times x squared all over m. Plugging in the numbers, we get 3 meters per second at point A. Not too bad yet, right? Same situation. Next piece of it. How long does a block spend as a projectile? And how far does a block travel horizontally as a projectile between points B and C? If you remember back to projectile motion, then you know that time can usually be found looking at our y-axis, the y equations. We're being launched horizontally, so our initial velocity in the y is 0. So we get these shorthand equations. Y naught equals 1/2 gt squared, and the range equation, x equals v naught times t. If our velocity in the y direction is 0, then all of our velocity in the x direction has to be all of the velocity. So if it's an initial velocity of 30 meters per second, then in the x direction it's 30 meters per second. We get t equals 0.4 seconds. Using the x equation to get the horizontal distance, we get 3 meters per second, that was the initial velocity, equals 1.2 meters is where it's going to hit the ground. Same problem. Next, what's the block speed just before hitting the ground at point C? What is the block speed just after hitting the block at point C? Let's use energy. So we're going from point A all the way to C. We don't care about B. That's okay. At point A, there's spring and gravitational potential energies. So we've taken that y equals 0 and we moved it down to the floor. We count gravitational potential energy now because it's going to change between A and C. Just before hitting the floor, the block has only kinetic energy. Very, very little height at this point. So we can say 0 height just before it hits the ground. So we have spring potential and gravitational potential at point A equals kinetic energy at point C. Can't cancel out the m's because this term does not have m. But we can plug in and solve for v. So we get 5 meters per second just before it hits the ground. Just after hitting the ground, it does not bounce. So its downward velocity is immediately lost and all of that kinetic energy becomes dissipated energy. In this case, it's going to be sound and thermal. Usually it's going to be sound and thermal. Because the block had a horizontal velocity of 3 meters per second at launch and the horizontal 3 meters per second stayed the same during the projectile motion, then the horizontal component of your velocity doesn't go away. Only the y component stops existing. So the speed of the block just after hitting the floor is 3 meters per second. See how the normal force is really large right at the moment of impact? The high normal force is what instantly dissipates all of that energy in the y direction. So it takes all of that velocity, all of that kinetic energy in the y direction, and sends it out. It also breaks your bones if this were your body rather than a block. Same problem, same situation, new problem. What is the coefficient of static friction between the floor and the gray side of the box? When it hits the ground, the block has a horizontal speed of 3 meters per second. The block only has kinetic energy, no gravitational potential energy, because we said y equals 0 on the floor. The block has no height and no spring potential energy. Spring is now at its natural length. It has nothing to do with anything. And then eventually all of the energy is going to be dissipated. So energy in the beginning would be the kinetic energy at point C, and the energy at the end would be the dissipated energy, which is force times displacement. In this case, the force dissipating the energy is friction. So we'll use friction, F sub F equals mu times normal force. The sliding distance was 3 meters. That was in the problem. Right here. Block slides 3 meters to rest between C and D due to friction. So when it lands, it's got that. Friction force is mu times Fn. Fn equals mg because it's horizontal and there's no other vertical forces and no vertical motion after impact. So our dissipated energy equals mu times mg times displacement. So we rewrite the equation and plugging in our numbers, m's will cancel out in this situation and we get mu equals 0.15. That was a really good problem at the end there. How'd you thinking? Please go do some practice.